Hello there. Today's video is all about solving the rotate array problem on the LeetCode website. As always, we're doing this in C++, and I'll give you a detailed explanation of the entire process, through the planning of the algorithm, to the coding of it, to the analysis of its time and space complexities, as well as looking at LeetCode rankings. So if that sounds good to you, then stay tuned. Welcome back. Now, this problem is going to be split up into two videos. In part one, this video, I'm going to go over 2 ways to attempt to solve the problem, and in the other one, I'm going to show 2 other ways. So to prevent spending like 40 minutes to an hour on this video going over all of the different ways that you could approach it, it's just better to separate it into 2 parts. So with that said, let's get right on to it. So we're going to be given an array, and we want to rotate the array to the right by a certain amount of steps, k, where k is a non-negative number. And we have handy-dandy examples here. So we are given an array with numbers from 1 to 7. Our k value is 3. So our output should look like this, with every single value in the original shifted over 3 places. And of course, if it would be a number that would shift beyond the end of the array, it would wrap around to the beginning. So, which is why 6 here, at the next to last index, will shift over 1, 2, 3 to wind up at the second index. And we see in the explanation what you would get for each of the baby steps that you do when you only shift it first 1 step, then another step, and then finally all the way to the end. And example 2 essentially does the exact same thing. So looking at constraints here, the length of the array that we can be given could be extremely small and only contain one thing, or it could be quite large. Values are the limits that integers can hold of the full range, and k could be 10 to the 5th or 0, and anything in between. Okay, now the follow-up asks us to come up with many different ways to solve it, and I kind of outlined that we're going to be doing this several different ways at the beginning, so we will eventually, through the process of creating these videos, get through several different ways to do it. And the other one is doing it in place with one extra space. And consider this statement some foreshadowing for the next video. Okay, so how do we solve this problem? Well, especially by looking at example 1 here, a brute force method that could pop into your mind immediately is essentially doing it like the explanation shows in example 1 here. Doing a series of baby steps, shifting everything 1 to the right, and doing that however many times until you get to k. Now I'll go over that code very briefly, because as you'll see, it's not the most efficient and definitely not the best way to solve it, but it is worth talking about. You can do the series of steps several different ways, but you're going to have some kind of nested loops, either while in a for loop, both for loops. It depends on the specifics of how you handle it. But your main goal is to swap each value with its neighbor all the way through the array, and then of course handle the wraparound that has to happen with the last integer becoming the first. With that brief overview as to the main logic of the code, let's go ahead and look at one implementation of that just right off the bat, since I don't want to spend too much time on this quote-unquote solution. Okay, some preliminary things in the code. First is an if statement to check if the size of the input array is equal to 1. If that's the case, we don't have to do anything, we can just simply return. Next up are some integer variables here. One named count, which is set to 0, and another one which is going to serve as a temporary holder. Next up is this line here, which adjusts k. k could potentially be larger than our actual array length. For example, we could have an array that only contains 3 numbers, but our k value could be something like 5. In that case, every time the k value is bigger, it's going to shift the numbers around until it gets to essentially one complete revolution, where you've shifted each of the numbers 3 places for that array of 3 numbers, so they're back where their original placement was. And then the 4th shift is essentially just equaling a shift of 1. Now, to adjust that k value, we can do this. We can set k to itself modulo num's size. So essentially, we want to divide k by the size of the input and then look at the remainder. And that remainder is going to be the adjusted shift that will fit within the size of the nums array that we're given. Then now that we have those variables and those conditional statements and the adjustments made, we start getting into the loop. And for this one, I decided to go ahead and make a while loop as the first one. You can implement it with 2 for loops. There are various ways to do it. I'm just going to show you one version of it. With a while loop that has a condition that as long as my count variable is less than k, we're going to go ahead and do stuff. And the stuff we're going to do is this code here. First up is temp holder is going to equal the value at the first index position of the array. So it's going to equal nums 0, which in this array here, for the example, would be the value of 1. Now that temp holder is holding that value, it frees this position to be replaced with the value that's present in the last index position. So num 0, this position here, is going to be replaced with the value in the last position, 7. So this becomes that. Now that I've done that wraparound, I can simply use a for loop to go through the rest of the array and replace the value at the current position I'm looking at with the value that came right before it. And the way I'm going to do that is by a reverse loop. So this is going to make it so that I starts at the last position, which we had freed up by moving it to the first position, and as long as the index is greater than 1, we're going to reduce I every increment. And what we want to do is replace the value at the current index we're looking at with the value that comes right before it. So in this case, we're looking at the last position here. We want to replace the 7 value with the value that's at the index that's 1 less than that, 6. So 6 is going to replace 7. 5 is going to replace 6, 4 is going to replace 5, and so on and so forth until we get to this point here, where our index is currently 2. And when it decrements down to look to see if this position needs to be adjusted via the code within the loop, we get to the index of 1. And that index doesn't need to be replaced by the value that's 1 below it. This one needs to be replaced by the value that's currently being held in that temp holder. And we can do that outside of the loop. So we only need to go until index is greater than 1. Then, after that for loop, we can simply have nums at that position equal the value of the temp holder. So that is now going to put 1 where it belongs. And we have, after all of that, done a complete shift of 1 step of the entire array so that we can count that shift that we've done. So count goes up to 1 from 0. And we do that however many times that we need according to k. And with that, the code is complete. And as we can see with running it, it will work for the most part. You can see handles this specific case well. And looking at this code, you can see that this if statement does indeed need to be there, because the way this nested loop is structured, we are essentially assuming there's at least 2 things in the array with making references to the first index and a second one. So if our given nums array only has one thing in it, this code breaks down. So this if statement does need to be there to avoid any errors out. So if we have a test case with that exact thing, run code, we will just get what we are going to expect with just having one, because we literally have nothing else to do. We could also have, say, this scenario where we have an array and we have a shift much larger than our array's size. But thanks to this line here, we can easily handle that as well. Pending judging, and you can see that we get the proper shift that we expect. So now that we've run a couple of test cases, before we hit submit, which you might have a sense of what's coming when we hit this blue button here, let's take a look at the space complexities and time complexities first. Space complexity is very good in this code. You only have integer variables that take up constant space, so your space complexity is a big O of 1. This is an in-place solution. However, with these nested loops here, a result of that is going to be a high runtime. This is slow. This is very slow. We have a while loop that is dependent on the number of shifts that we need to do, and we have a for loop that is essentially dependent on the size of the array. The bigger the array, the more iterations this for loop has to run. The bigger the k value, the more the while loop has to run. So this is a big O of n for the input array size times k, which is the number of shifts that you need to do. Now, that's all well and good, but as you probably can guess, look what's going to happen when we submit. Judging, time limit exceeded. Yep. This is a brute force method. It's something that can easily pop into your head, and it does work for small input array sizes. But as you increase all of those mini baby steps that you need to do for the array, if you have a really large array and a lot of steps to do, this is going to take a lot of time. So this could potentially work for small input cases. It could be something that can be asked of you initially in a technical interview, and you're given ideal constraints and scenarios for it. But when you create something like this, an easy follow-up line of questions to it could be, hey, what are the shortcomings of this code? Which is, yeah. So how can we make it faster? Well, another thing that might have popped into your head is solving this problem by grabbing some additional memory. Essentially making a new vector that will house the rotated array and populating it as you go through the original array. Essentially, you would start looping through the original array, and you would input those values into the new array, starting at a specified position that is equal to the number of steps you need to do. So bringing up my handy dandy whiteboard, it would essentially look like this. You have your original array. We have the new array that will house the rotated values in their final positions, and it's pre-sized to equal the original array, which means it's initially filled with zeros. What we want to do is, as we go through the original array, we want to populate the new array with those values, starting at the k value. And we want to go as long as we don't hit the end of that new array. When we do, we want to reset our position in said new array, continue looping through the original one, and fill out the rest of the values. So that's the logic for it. So let's go down here, reset, and start creating that solution. First part of the code, since we are using additional memory to help us solve the problem, we're going to create a new vector of integers, and I'm going to call that rotated nums. And this array is going to be set to a size that equals the original nums array. We're going to do the same adjustments to k that we did in the previous quote-unquote solution, where k is set to itself modulo nums size. And we have a integer variable termed position, and I've set that equal to k after I've done the adjustment. Finally, we have the beginnings of a for loop, which is just the typical for loop. We start at the beginning, we go to the end, we increment up by 1. Within the for loop is going to be some if-else statements. If our position variable is less than the new array's size, rotated nums, then we haven't yet reached the end of that new array, and we can just go on ahead and set the value of rotated nums at that position to equal whatever the value is at the current index in the original array that we're looking at. And of course we want to increment up position as we do it, so that's why the plus is there. Now, if this condition is not true and we are at the end of the array, we want to reset position to be 0. We want to wrap around and start filling out the values at the beginning. And then we do the exact same thing. We set the value at that position to whatever value we're currently looking at as we loop through the original array, and we want to make sure to increment up position every single time. The final thing to do is, because this is a void function, we need to set our original nums array to equal our new rotated nums. And with that, this code should work. So let's first run the code. We're going to be doing this custom one, which works perfectly. So let's go ahead and hit submit. Pending, judging, accepted. So much better than the red text. Okay, before we look at the rankings for this, let's go over time and space complexities. Space complexity is worse than the previous code. The first solution attempt was an in-place one, so it didn't need to carve out variable extra space that is dependent upon the nums array size. This one does, however, so its space complexity is no longer constant, and it will be on the order of big O of n, where n is equal to the input array size. However, our time complexity, and as the green text indicates, well, we're faster now. Instead of having a nested loop, we only have one for loop. So we are only dependent on the nums array size. So we went from a big O of n times k time complexity to a big O of n time complexity, which is much, much faster when dealing with large dependencies here. And why we got green text when the other one failed via taking up too much time. So, big O of n space complexity, big O of n time complexity. Now let's look at the rankings. Okay, we are somewhat lower on the rankings here. Looks pretty much like a bell curve and not too many differences in runtime, so I can expect some potentially significant ping-ponging to occur. Memory. We are fairly low on the rankings for that, which makes sense because we're using a method that takes extra memory and is not an in-place one. So I would expect to be able to ping-pong somewhat around this distribution, but never get to this area where probably the in-place solution answers are. And with that, we have seen 2 attempts at solving the rotate array problem. The next video is going to show off 2 other solutions that will improve upon the memory usage at the same time as trying to keep it as fast as possible. So I hope this video was useful for you. If it was, consider subscribing, and as always, I'll wish you a happy coding and to have a nice day.